About a year ago, I embarked on a journey. This was a journey that had the potential to affect the rest of my life. We've all had moments like these in our lives. A job interview that needs to go well, a fiance, hopefully, that needs to say yes, or our first piece of code that makes it into production, that needs to not kill a bank. In many ways, my journey was very similar to these. It was my degree. I was in the final year of my computer engineering studies, and the only thing standing between me and a shiny new degree, or at least a nicely printed piece of paper, was my final year project. Now, this project stood in front of me like an absolute mountain. Never before had I had such an important event in my life. And to make matters worse, or at least more stressful, I had the absolute privilege of being given a bursary by a fantastic software engineering company that I was very excited to join. Can you imagine the phone call that I'd have to make if I didn't pass, and sort of how that phone call would go? Hello, BBD. Yes, so I won't be joining you next year. Why? Well, I'm enjoying my studies so much that I wanted to do it again for another year. Luckily for me, I only failed 2 modules during my studies, and my argument is always that I enjoyed them so much I wanted to do them again. From a young age, I've always loved building things. My dad is a mechanical engineer, and together we've taken apart everything, cars to kettles. It's from him that I learned the value of voltage and current after accidentally connecting a 12-volt receiver to the 250 volts of our house and having it explode with such force that it broke the light hanging above our head, which proceeded to then come crashing down at our feet. So when the project selections came around, I knew I wanted a project where I could use my hands to build something. Now, one thing led to another, and the end of a rather long story is that I ended up needing to build a handwriting robot, a robot capable of replicating the handwriting of a real human being. Now, I asked AI what a robot like this would look like, and this is what I got. I'm not entirely sure how accurate that is. Luckily for me, I have been blessed with terrible handwriting. Bad enough where I even contemplated becoming a doctor just so that I would fit in. Handwriting so bad, not even a paleographer would be able to understand it. Now, for those of you not versed in the realm of scriptural exegesis, a paleographer is someone who decrypts and deciphers ancient handwriting and manuscripts to understand documents. And basically, my point is that my handwriting is super bad. Now, this, combined with the threat of future joblessness, inspired me to tackle my project head on. Hi, my name is Stefan De Jager, and luckily I never had to make that awkward phone call, because after successfully completing my project, I have recently graduated from the University of Pretoria with my degree in computer engineering and joined BBD as a software engineer. Through the journey of building my robot, I had many challenges that I had to face, many struggles I had to overcome, and many lessons that I had to learn. Now, I would like to take you through this journey with me and share some of those lessons that I learned. Where should we start? Well, where any good story starts, at the beginning. First principles, specifically in engineering, means starting from the most basic facts and building up from there. First principles are to engineering concepts what grassroots are to political concepts. They are also heavily emphasized during engineering and are a strict requirement of all final year projects. Many of us would have learnt about first principles, whether it's in our job or our studies, and they honestly suck. But let me not get ahead of myself just yet. To build a handwriting robot, we need to start at the end. Now, the fancy engineering phrase for this is top-down design, bottom-up implementation. So, starting at the top, what is everything that we want this robot or system to be able to do? Now, for us, that's easy. The system needs to replicate the handwriting of a human. Once we understand the end goal, we can start to split things up. So, let's split that up. Well, since it's a robot that needs to do handwriting, we would naturally need a pen. So let's start there. Now, a pen is great, but it can't really do anything unless you move it, right? It's sort of like a bicycle without pedals. You might look cool standing next to it, but you're not going anywhere without a little help. So how do we move this pen? What do we know in our world that can move things? A car, a bus, an elevator. They move things all the time, right? Up and down, all day long. What about another person? Okay, I'm going to ask my lovely long-haired assistant to please come up and demonstrate my point. Can you please write your name and what you had for breakfast this morning? Ensue awkward silence as we all stare at you. No pressure. What is that? 3 shots of tequila. Whoa, hey, like it. Thank you very much. No, my pen, go away. Ladies and gentlemen, handwriting robot version 1. It's voice controlled. It does whatever you want it to do. Thank you very much. I will be here all week. Maybe we need to narrow down our search. Do we have any existing technology that's similar to what we want to achieve? 3D printers. FDM 3D printers can accurately control the movement of their nozzles to print in high detail. This is perfect. Okay, let's build a 3D printer. Now, how do we do that exactly? Well, a 3D printer can move its nozzle up and down, and it does this by, there are many ways to do this, but luckily for us, we only want to move a pen. And so up and down can be treated like a Boolean. You are either touching the paper or you are not touching the paper. 3D printers can also move their nozzles left and right, and they do this by using bearings that glide on rails and all wonderful engineering concepts like that. So we now have a system that can move our pen, but sadly it's like a car with no engines. So let's add some engines. Or to be more accurate, let's add some motors. Since we want to accurately control the movement of our pen, I'm going to opt for some stepper motors. Now, stepper motors are great because unlike traditional motors that just spin around and around, by carefully controlling the voltage on each of their input wires, we can get them to move an incredibly small distance and then stop. 0.9 degrees to be exact. How do I know that? Well, trust me, I'm an engineer, but also I read it on the side of the motor. And it's through these incredibly small distances that we can accurately control the rotation of the motor and in turn accurately control the movement of our pen. We now have all the parts that would allow for movement. Our pen can be moved up and down. It's nicely sitting on some rails with some bearings and some motors so it can move left and right. But we have nothing to control the actual movement. So let's write some code. Believe it or not, but even something as complicated as this can even use an Arduino. Now, for those of you who might not know what an Arduino is, it's like a very small, very powerful, but very stupid computer. It has these pins on it called GPIO, or general purpose input-output pins. And using some very basic code, we can get it to turn these pins on and off. Doing that, we can control the motors and get them to move how and when we want them to. Behold our robot. We have a pen, we have stuff to move the pen, and we have stuff to control the stuff that moves the pen. We now have a pen that can, in theory, move, but movement is just one small step required in handwriting. We still need to figure out how to capture human handwriting in a way that the system can understand and write it. My idea for the solution came from a projector. Have you ever really looked at a screen like this up close? From where some of you are sitting, you see an image of smooth lines. But from where I am, real up close to the screen, I see pixels, many tiny little squares that all come together to give the image of smooth lines. Let's use that as a base for controlling our pen. This image looks normal and natural, but there are actually no smooth lines anywhere here. What if, given an image like this, we have the pen dot on each black pixel, and in that way we can draw or write something? Let's try that. Let's build a system that takes an image, which is just a 2D grid of squares, and has something that finds a black pixel, moves the pen to that point. We then dot and lift the pen and repeat the process until we've drawn on everything. This works great, but it results in something that looks far from actual human handwriting. You see, this is because humans write by keeping their pen on the paper and finishing a letter. So maybe lifting the pen the whole time wasn't the best idea. Maybe we should try bring our implementation closer to what humans do and keep the pen on the page for longer. We can achieve this by following a special procedure. Given an image, find a black pixel, move the pen to that point, put the pen down, look around the pen for any other black pixel, move the pen to that point. Look, move, look, move, look, move. We continue this until there are no more neighboring black pixels that we haven't drawn on already. Then, and only then, do we lift the pen and repeat this process. Now, this slide explaining all of this would have been really cool, and it would have had like animations in it, and it would have made so much more sense, I promise. But sadly, my PowerPoint skills are as bad as my handwriting, so this is what we get. If we put all these pieces together, we end up with a robot that can draw or write some image. If it's an image of a house, we can draw a house. If it's an image of someone's handwriting, we can write that too. But I know what you're thinking. What does this have to do with writing the handwriting of a human? I mean, all we can do is just copy a picture. Well, this is where the magic of cameras comes in. To start the process, we first need an image of someone's handwriting. For this demonstration, I have a sample of this person's handwriting. For those of you who may not know who this person is, his name is Kevin Staples, and he is the CEO of BBD. Like me, he is also an engineer, but he's one of those electrical kinds, and so despite his disabilities, he's made it rather far in life. I thought that he would be the perfect person to use for this demonstration for reasons that we will see later. Once we have a picture of the handwriting, we need to get it into a form that the system can understand it or use it. The images that we take of handwriting technically are full of color. Some spots might be a little brown, others slightly red, and there are a lot of shades of gray. Now, we don't want that. We want the white of the paper and the black of the pen. So we need to binarize our image, meaning that every sort of white pixel gets converted to white, and every sort of black pixel gets converted to black. That way, we end up with an image that's made up of only two different pixel values, black and white, with nothing in between. Okay. Like any typical client on any typical project, I'm now going to throw a metaphorical spanner into the metaphorical works and slightly clarify the goal of our robot. You see, earlier I explained that the system needs to replicate the handwriting of a human. Now, sadly, this isn't as easy as just copying what they have already written down. Instead, the system actually needs to produce new pieces of handwriting in the handwriting of a human. Like some of you here, when I got this slight requirement change to my project, my first thought was, what? You want me to do what? How? I then had to take a nice long sit down for the sake of my own mental health and sanity and think of this new problem in front of me. How is it possible to take someone's handwriting and write something completely new that they have never written before? I mean, to do that, I'd need to teach the robot how someone's handwriting looks. I'd need to build a custom sentence based off of that person's handwriting. Okay, wait, but at that point, the handwriting is just a picture. And we already know that our system can draw pictures. Okay, new goal. Let's get the system, or let's make a system, that takes someone's handwriting and saves templates of how a specific person writes their letters. That way we can use those templates and put them together in any order to make any sentence that we want. The first thing we need to do is to get a sample of a letter of a person's, or a sample of each letter of a person's handwriting. The quick brown fox jumps over the lazy dog is a fantastic sentence since it uses each letter of the English alphabet. If we can get someone to write out this sentence, once in lowercase and once in all caps, we then have a sample of each letter in their handwriting. Okay, let's try that again. I now have my quick brown fox in Kevin's handwriting, and just like last time, we start by taking a picture of it. Next, we need to binarize our image, and we now need to extract each of those letters so that we can use them later. Now, we can achieve this by using several actions typical of any computer vision problem. Now, these were all a giant pain for me when building my project or doing my robot or whatever, because I had to implement all of them from first principles. First, we do edge detection on the image, where we figure out where one letter starts and another letter ends. It's important for us that our letters don't touch, or else we might not properly be able to tell them apart. Next, we perform contour extraction, where we trace around the edge of each of our letters so that we can crop them out and save them into their own image. And now we have these. Since we know the sentence that our subject wrote, we can also label each of the letters and images that we take out, and that makes storing and retrieving them a whole lot easier. Now, these letters that we've just saved, labeled, and stored, can now be put together in any order to make any sentence that we want. And for those OCD people out there, these aren't all of them, these are just the ones that I used for the slide. To make a sentence, we first need to get a sentence that we want to write. I think tomorrow everyone gets the day off. Now you can see why I wanted Kevin's handwriting for this. But for those of you saying, Stefan, I don't work for BBD, can I still get the day off? Yes, absolutely. Come see me afterwards. I'll give you your own personal letter. You can take it to your boss tomorrow, and they will have to give you the day off. I mean, come on, it's written by the CEO of BBD. Hello. Each of those letters that we've saved earlier then get put together to make our sentence. This sentence generation process caused me some problems when making my project. The main problem being is that you can't just place letters next to each other. Instead, some letters need to be shifted vertically, either up or down, to match with the other letters in the sentence. To solve this problem in a dynamic way that would hopefully work for each person's unique handwriting, I grouped letters into 3 different categories. These are risers, fallers, and neutrals. I know, very scientific names, but bear with me. It's the kind of classification that only a true genius or someone with a fondness for complex oversimplification would come up with. Now, before we dive in, let me preface this with a disclaimer. I am not exactly a font expert, so please do not expect any beautifully crafted typefaces. My handwriting is already legendary for all of the wrong reasons, and let's just say my font knowledge is about the same. So if you were expecting a masterclass in typography, I'm going to need you to adjust your expectations down, way down, like all the way down. Okay, first we have risers. These are all the letters that go up. Think F, L, H, D. All capital letters are also automatically risers. Then we have fallers. These are all the letters that go down, think Q, Y, P. And lastly, we have neutrals. These are all the letters that don't go up or down. Think A, E, O, U, R. Basically, if it isn't a riser or a faller, then it's a neutral. Along with grouping the letters into their 3 different categories, I also used a special 3-line system to go along with it. When making a sentence, imagine that there are 3 lines in a row. Neutrals get placed with their middles on the middle line so that they all nicely line up with each other. Risers get placed with their bottoms on the bottom line so that they align while their tops can do whatever. And lastly, fallers get placed with their tops against the top line so that their bottoms are left dangling below the rest of the letters. This 3-line system isn't perfect, and I still have sleepless nights over how I can possibly improve it, but it's good enough for most people's handwriting. I mean, it does give problems on handwriting that's super big or super small, but generally it's okay because most people's handwriting follow these rules. Putting all of these new rules into place, categorizing our letters using a 3-line system, we end up with a sentence that looks like this. Okay, so now we have a sentence that's made up of Kevin's handwriting, but we can't write it just yet. See, looking at this image, we see that it's made up of lines. To our eyes, they're just lines. But for a computer, these lines are made up of pixels, all nicely lined up next to each other, which give the lines width. This is a problem for us since what we've discussed earlier is we know that the system is going to try to draw or write on each black pixel that it finds. This is a problem since the lines that we want the system to draw have width. We will end up with the system needlessly writing lines wider as it tries to fill in this width. The solution for this problem is to make sure that each line is only 1 pixel wide. In that way, the robot goes up and down instead of needlessly going sideways. We can achieve this by using what's called a thinning algorithm. Now, frankly, I would love to say that I came up with the idea of a thinning algorithm, but no. The algorithm that I used is called the Zhang-Swen thinning algorithm. And I would love to explain to all of you how and why it works, but I'm pretty sure I'd need to sell my soul to be able to understand that. The only reason that I was able to implement it myself was because of some very useful online articles, Google and ChatGPT. But nevertheless, we have an algorithm that turns our sentence into this. The same thing, but each line is now only 1 pixel wide. Now it's finally time to write our sentence. Hint, hint for the tech people. I just need to make sure that it is actually turned on. That will be so much better. And go to the thingy. Where is my mouse? There you go. You are turned on. There is a pen. There is paper. And so I'm going to need you all to pay attention. It's going to happen pretty quickly. So it starts by establishing a serial communication with the robot. It then calibrates itself by going into the top left corner of the page. This is because most of our writing starts in the top left. And it then follows that procedure that I explained earlier. So it finds a black pixel, puts the pen down, traces along until it can't find any more black pixels that are directly next to where it is, lifts up the pen, and continues this process, finding the next black pixel, following it, and continuing on. Now, this will result in something that looks like human handwriting or traces like human handwriting, but it writes letters in a weird order, where it sometimes writes half of a letter or a portion of a letter, and then the next closest black pixel is one that belongs to another letter. And so it'll start writing another letter, leaving half a letter just existing until it eventually comes back and finishes it. One of the main things I wanted to overcome with this was not write like a printer. So printers are easy. You can dot, 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 and do that. But that's just a printer. I wanted movement and tracing. And just like that, we are done. Let me just take this out so we have proof that it has done its thing. Congratulations, everyone. It looks like we all have tomorrow off. Go back to my slides. Now that we've covered the robot, let's actually get back to first principles. Engineering teaches us the value and necessity of building and designing things from first principles. You need to have a fundamental understanding of how certain things work to be able to build certain systems and work with certain technology. This process, although well-intentioned, without a doubt has its downsides. And it's these downsides which hamper human growth and ingenuity. Cars are the perfect example of this. I love to drive a car, like many do. But how many people do you think fully understand, oh no, my slides are gone? Let's see. Oh, they're back. Okay. Okay. Let's go slightly back. So, I love to drive a car, and I'm sure many of you also do. But how many people, and that's behind. Oh. Okay, that's fine. It's going to freak out later. But how many of you fully understand the theory behind the modern combustion engine? Or what about the math required to determine the correct axle thickness to prevent drive shaft breakage due to high torque acceleration? I mean, almost no one, right? Well, literally no one. I made up that last example. But that's exactly my point. To drive a car, to love driving, I don't need to know these things. Yes, it's important for someone to know them, but not the end user. This same approach should be taken for technology. I don't need to understand how Flyway is performing its database migrations on a register level to effectively use it. Having something like OAuth to manage the login and passwords of users abstracts away the extreme complexities of security, something that I am no expert in. I don't want to have to worry about how my compiler is optimizing my for loop that I just made. But nevertheless, I'm using that capability and bearing its fruit. As the creators of tech, and often very complex tech, we need to ensure that we abstract away as much of the complexity from our users as possible. This includes complexity not only in using our systems, but in integrating their systems with ours. See, we're a few slides behind, so it'll catch up. All that having this confusing tech exposed to the users does is it creates barriers for entry and barriers for usage. Imagine having to understand angular momentum to be able to get into your car and drive to work in the morning. Throughout our lives, we've already done away with the ideas of first principles. From an engineering background, we're taught that everything should be from first principles. But through building this robot, I've learned that the way we build and the way we work are not how we're taught. This robot of ours that we've just spent the last 20-something minutes of our lives building is the perfect example of this. Even in a system where everything needs to be from first principles, there are many aspects that aren't. Imagine how much longer the system would have taken us to build if we first had to understand the theory behind how stepper motors work, or how to build our own working stepper motor. Do you think we'd be able to achieve the 0.9 degrees accuracy of a commercial motor? I mean, I think not. Even within the robot, as soon as we finished a subsystem, we immediately abstracted away that complexity from ourselves so that it would be easier to integrate with the other subsystems later. We started with a pen that needed to move. Once we figured that out, we could forget about all the bearings and rails and motors and just focus on the code for controlling them. Once that was done, we could even forget about the code and just focus on how to get handwriting into our system. Once that was done, all we needed to pay attention to was how to make our own sentences. And once that was done, all we needed to do to use the system was take a picture of someone's handwriting, type a sentence, and press a button. This task that previously seemed impossible at the start now boils down to 3 simple steps. And if you wanted to extend the system further and expand its capability, making it even cooler, all we'd need to do is build on our previous level of abstraction. If we wanted to make this robot smart, we could add speech to text which would just replace us having to type the sentence that we want. So, what now? Where does this leave us? Should we just do away with the ideas of first principles? Toss them aside like the baby with the bathwater, never to be seen or heard from again until they fade into mystery and become nothing more than a myth like the lost city of Atlantis? Well, no, not exactly. First principles, like many things, are good in moderation. A good servant, but a bad master. They're like marshmallows. One or two and you're fine, but after a whole bag full, you're left feeling all sticky and gross. First principles should be treated as domain specific and should only be implemented and considered within their relevant domain. The best way to understand this is through the use of an example. Let's say I was busy building a library. This library deals with sorting. It sorts arrays, it sorts lists. Gosh, it can even sort M&Ms. And it has a whole list of wonderful algorithms that users can choose from when using it. Now, within the domain of me creating this library, I would probably need to implement those sorting algorithms from first principles. But I wouldn't require my end users, those using the library, to worry about those first principles. They wouldn't need to understand my implementation to use my library. All of us, as creators, as technologists, the complicated technology that we create can be hard to understand, but should be easy to use. The brilliance of innovation lies not in constantly reinventing the wheels, but in building on the works of those who came before us. It's about knowing when to implement first principles, and when to abstract that complexity away and stand on the shoulders of giants to reach even higher. Isaac Newton once said, "If I have seen further than others, it is by standing upon the shoulders of giants." The next time you create something, anything, spend some time thinking about the first principles. They're our foundation, our roots. But remember, roots are only the beginning. It's what grows from them that truly matters. Where would you be if you had to keep reinventing the wheels in your life? And where could you be if you really leaned into innovation and strived to build on the works of those that came before you? In the end, it's not just about the technology that we create. It's about how we use that technology to move forward. And if we do it right, we won't just be making robots that write, we will be writing the future itself. So as you leave here today, spend some time thinking about the projects you're a part of, the systems you work with, and the innovations you're driving. Ask yourself, are you being bogged down by this need to constantly understand every detail, or are you leveraging what's already out there to build something truly remarkable? Are you clinging to this idea that you must master everything from the ground up, or are you willing to stand on the shoulders of giants and push boundaries further than what you thought possible? Innovation isn't about doing it all yourself. It's about collaboration, about building on what exists and making it better. It's about recognizing that progress is a collective effort, one that's built on the knowledge and achievements of those that came before us. So let's embrace that. Let's continue to build, to create, to innovate, and to push boundaries, not by endlessly retracing our steps, but by boldly stepping forward, confident that we're building on a solid foundation. And who knows, maybe one day the systems that we create will serve as the foundation for future innovation, inspiring future generations to reach even greater heights. Thank you, and here's to the future that we will build together. People have questions? Do we have mics? Oh, we have mics. Whoa.
Oh, thank you. You mentioned in your talk that the handwriting you trained on had to be separated. So, what changes do you think you'd have to make to deal with cursive handwriting or signatures?
Sell my soul to Satan. I was thinking about that. So one of the things that I thought about looking at, but I sort of ran out of time through the whole project, was if you, once you've contra extracted out, let's say we have two letters next to each other that we now think is one letter, you can look at the ratio between the height and the width and see if the width is way too big, you know that there are two letters there. And at that point, it's a process of looking at how many black pixels do you have in each column and figuring out where's the least and sort of hoping that that's the split between two letters and sort of just chopping it off there. But like I said, I like my soul, so, you know. Any other wonderful questions? Anyone who would like their own personal letter, please come see me. I will give you one, and you can have the day off. Woo, I think that's us. Thank you, everyone.